Hi everyone, I'm really glad to be here. I'm Carlos Rocha. I'm a research software engineer at the Netherlands eScience Center. In this talk, I will give you an overview about QC2, a modular open source software for quantum chemistry with quantum computers. Before going on, I'll be giving you an overview about my organization. The Netherlands eScience Center is the center of expertise in research software in the Netherlands, and we are founded by the Dutch Research Council. And the Netherlands Science Center is centered around two main ambitions. And the first one, we work with researchers collaboratively to develop open source research software. And this is done via open code or even external projects. In the second ambition, we build and seek to provide digital expertise for researchers in the Netherlands. And for this, we also provide workshops ranging from basic to intermediate Python, good practices in software engineering, and also more involved topics like CUDA programming. And QC2 is a direct outcome of one of such projects, QC4QC, which is collaborative effort between the Netherlands eScience Center, SURF, and FU Amsterdam. The main objective of this project was to develop a dedicated software that I'll be referring here as QC2 to facilitate the interoperability between traditional quantum chemistry codes and Python quantum computing libraries, essentially to facilitate users to perform quantum chemistry calculations using quantum computers. Quantum chemistry may be used in various contexts and show several bases as well. So there are researchers that are interested in studying very big systems, for example, like the folding of protein. And for these systems, because they are so big, the researchers have to rely on very approximate mathematical or physical models, for example, relying on classical mechanics. For other medium-sized systems, we can indeed apply some formally, physically, mathematically sound quantum mechanical or quantum chemistry methods like density functional theory. But it is for these smaller systems that we so far can apply or test the most accurate state-of-the-art quantum chemistry and quantum mechanical models. And these are the ones that QC2 is currently dealing with and that I will focus during this presentation. Atoms and molecules are indeed true manifestation of quantum objects, and they show characterized by discrete energy levels that are actually the discrete spectrum of the corresponding molecular Hamiltonian. And this can be naturally described by solving the corresponding Schrödinger equation that I show here in a very simplified form. So as you can see here, this is an eigenvalue problem where A is the molecular Hamiltonian, C is the corresponding wave function of your system that completely describes your target molecule, and E is the associated discrete energy associated with this wave function. Unfortunately, this equation can only be solved exactly for one electron systems, for example, like the hydrogen atom. And for all other atoms and molecules, we must rely, therefore, on approximate mathematical and physical models that seek only to approximate the exact solution of the Schrödinger equation. Perhaps among the most popular strategies to perform these approximate solutions in quantum chemistry, and perhaps also in quantum mechanics, is by resorting to the so-called variational principle. And here, the unknown wave function of your system is approximately given as a linear combination of known basis functions, and the corresponding coefficients are then obtained in a variational manner in such a way to minimize as much as possible the energy or the ground state, the most stable energy of your system. Essentially, when you are resorting to the quantum chemistry method based on the variational principle, Your classical computers are essentially trying to diagonalize very large, very rich matrices, and in such a way as to obtain a diagonal matrix containing the corresponding eigenvalue, energy values of your ground state or even excited state system. This process consists certainly the computational bottleneck of classical computers. So just to give you here some idea, one of the prime or most accurate methodologies to find the ground state or even side state energies show exponential complexity in relation to the number of the electrons contained in your target system. Okay, now that you have overall idea on how we approach quantum chemistry using classical computers, let's try to then start approaching how we use then quantum chemistry and quantum computing to also perform approximate solutions to the Schrödinger equation. In the noisy intermediate scale quantum era, quantum chemistry is traditionally approached, and the approximate solutions to the Schrödinger equation are traditionally approached using hybrid quantum classical algorithms like the variational quantum eigensolver, in which QC2 and several other Python quantum computing libraries are primarily based on. As you may know, in this algorithm, we start with a set of qubits in specific appearance or initial states, and to this we apply a variational form that contains a series of quantum gates that depend on certain qubit rotation parameters. So if this parameterized quantum circuit and associated appropriate form of the molecular Hamiltonian, we are then able to measure the expectation values, or in simple words, the energy of the molecular system that depends on the circuit parameters. This is obviously a cost function that we can be optimized resorting to or using an external classical optimizer that will then guess the best meters which to evaluate the circuit. So this process continues on and on until we obtain via convergence the lowest possible energy of your system. I'm not going deep into details, but I just would like to let you know that QC2 and any VQE algorithm need some initial information to start with. And when we are talking about quantum chemistry, this initial information can only be done by running or by resorting before that traditional quantum chemistry goals. This will supply information like those needed to, for example, the buildup of the reference quantum circuit, and also some physical information that will be later on, or physical quantities that will be later on be used to build up the molecular Hamiltonian in qubit representation. It's obvious that we need to provide a proper variational form or ansatz that will be used. And in quantum chemistry, it is very traditional to use physically motivated ansatz like those derived from direct couplet. Just to give you some overview here of the core design principles of QC2. QC2 has been primarily designed to leverage existing tools, and as I'll be discussing later on in the next slide, it uses very popular quantum chemistry Python libraries like atomic simulation environment calculators, and also standard data schemas to offload the necessary information, initial information, to build up the quantum algorithm. Also, QC2 is designed to smoothly integrate with popular quantum computing libraries like QSkit Nature and Pennyline QCAN. QC2 is also designed to be highly modular and features a built-in algorithm package that is designed also to make it easier any extension and enhancements in the future. It's also very user-friendly and has a very intuitive interface, as I'll be discussing later on, that enables users to focus on that research, obviously, with minimal technical details. Here, just give you an overview also of the workflow of QC2. As you can see here, for example, QC2 uses Python bindings or custom atomic simulation environment calculators that run on the back behind the curtains your preferred quantum chemistry program. This will then, the SE will then get the relevant information and save this into formatted data files that will be later on read by QC2 to, for example, to build up your reference quantum circuit, your molecular Hamiltonian and qubit representation, and also instantiate algorithm classes that will then be run using QC2 and Penny-Lane QK. Here I just give you a very minimal input of QC2 to perform a VQE calculation on water. So as you can see here, after importing some important modules, the key aspect of QC2 here starts with instantiation of a QC2 data class that will contain information about the target system that we want to deal with, and also provide a file name in which will be all the output of the calculation will be saved and might be also used to restart a new calculation. The second step here is to specify and run an appropriate custom QC2 ASE calculator for your preferred quantum chemistry goal. Here I'm just using the one from by SCF. Here we need to instantiate the corresponding algorithm class that will also be run afterwards, and that's it. Very simple and very straightforward. Here also I show another input which now uses or performs an ortho-optimized VQE calculation, which is an extension of VQE, in which we are not only here optimizing the circuit parameters, but also allowing the initial molecular orbitals to be relaxing throughout the calculation. And as you can see here, the structure of the input is exactly the same. The only difference here that we are now instantiating the corresponding OO VQE class. And this certainly reflects the modularity of QC2, in which we can play around with some blocks or some pieces and maintain the same structure of the input. Finally, I just show here some representative benchmark results using these QC2 input examples. And here I show the ground state energy convergence of water in its equilibrium structure as obtained with QC2 using a CQE algorithm and ortho-optimized VQE or OO VQE using also QC2. Also here I show the expected converged energies of ground state water as obtained using traditional quantum chemistry methods. And as you can clearly see here, the OO VQE energy is variationally well below the corresponding VQE as expected, right? And converges quite nicely and is nearly exactly to the traditional energy obtained using CAS-SCF. So just a final remark, QC2 is an ever-growing open source project that is constantly being enriched by new algorithms and new features. And as an open source software, we are warmly welcome any type of contribution, either if it's on comment, new ideas, new approaches, or even full PRs. And here I put the link, full link of QC2 GitHub, free to go and visit and make your contribution. And thank you very much for inviting me, and I wish you all an amazing Conf42 quantum computing Congress.